Next up, we are going to derive the definition of resistance. Now, this is what you have probably used last year and is very commonly called Ohm's law. I equals delta V over R. That is what we're about to derive right now. And what we have right here is I've got V is electric potential. This is V initial. This is V final. If charge is moving, positive charge moving to the right, this is high potential, low potential. That's cross-sectional area A right there. This is length L. Now, delta V, the change in potential here, is equal to, and what form did we see this in before? Delta V equals EL. That's just the magnitude, by the way. Yeah, delta V is negative, Ed. It is negative. I'm just looking for the magnitudes here. So the magnitude, and I should probably put that, magnitude of delta V is ED. In this case, I've called it the length L. So it is EL. This only works for what kind of a field? Uniform field, which is what is in here like this. There is a uniform field inside this. And again, fields can exist inside conductors as long as they're not in electrostatic equilibrium. So the electric field strength is delta V over L. Again, this is the magnitude. And this is the magnitude of that, magnitude of that. And notice that using Ohm's law here, I can solve for the electric field. And this is just sigma. The current density is sigma times the electric field. That's what I got here. This is the electric field right there. That. So since the current density is the current per unit area, continue to here, because J equals I over A is equal to this that we have right here. That's J. That's equal to I over A right there. And then I can just solve for delta V over I. It is the length over sigma times A. Because 1 over sigma is the resistivity, here's what we get. And this is kind of the bottom line, what we have here, is delta V over I is this. Delta V over I is equal to that right there. Rho times the length. Rho is the resistivity. This is the length of our section. This is the cross-sectional area. So as long as I define resistance like this, if I make this the definition of resistance, then I've got what we used to call Ohm's law, which is really just a way of looking at what resistance is. Resistance is the ratio between delta V over I, but I can calculate it like this. And I'm going to show you guys the meaning of this with a cool demo right now. Notice our resistance depends on 3 things. It depends on rho, the resistivity, which depends on what? What does resistivity depend on? The material only. Depends on the material, but it depends on the length and the cross-sectional area of my sample. Let's go ahead and do a demo that shows that. Well, what I have is 3 different conductors, and what we're going to have is airflow here. I've got a long one, I've got a short one, but they have the same cross-sectional area. And I've got one that's the same length as this one, but it's got a narrower cross-sectional area. So let's try each of these things one at a time. Let's ask, I think this might be easier to understand. Which one is going to more easily allow airflow? The wide or high cross-sectional area or the low cross-sectional area? Go ahead and make a prediction and we'll find out. Okay, so we're going to watch. Let's do the low cross-sectional area first. I'm going to connect that right there and we'll watch how long it takes this balloon to drain. It's going pretty slow there, but we can confirm flowing really, really slow out this end there. Okay, so I think we got the idea here. Now I'm going to try this. Same length. This one's the same length, but it's a much wider cross-sectional area. Same length, wider cross-sectional area. will this be faster or slower than the other one? Sure enough, this has less resistance to airflow, just like a conductor would have less resistance to electron flow if it has a greater cross-sectional area. So is cross-sectional area proportional to resistance or inversely proportional? The bigger the area, the lower the resistance. Now we're going to try length. So I've got this very long straw, same cross-sectional area but different lengths. So we'll redo that. Redo this one just so you remember how quick this is. Okay, here we go. And it drains out and pretty fast. Now we're going to try the same one, same cross-sectional area, but much longer. Would you predict greater rate of flow or lower rate of flow? Let's see what happens. And here we go. It is draining. Is that faster or slower than before? Slower. It's slower. So does this one, this longer one, have greater resistance, thumb up, or less resistance than this one? The longer one has greater resistance. There is more friction felt at every point along this because it's got to get through a longer piece. And that is actually the same thing for heat flow if you're in the B class. The longer it is, the longer it takes heat to travel through. The longer it is, the harder it is for electrons to get through as well. That is a perfect explanation about why this equation right here is true. The resistance of a sample. Notice you cannot answer the question, what's the resistance of copper? You can't answer that question. Can I answer the question, what's the resistivity of copper? Yes. But if I gave you a sample of copper, you could measure the resistance of that. Resistance is proportional to the length, it's proportional to the resistivity, but it's inversely proportional to the area. So here's an example right here. Find the resistance of it's a composition resistor of carbon. It's a carbon cylinder. It's 2 centimeters long, and the radius is 1.5 millimeters. Now you need the resistivity table, which is in your textbook for this. The resistivity of copper. Notice the units of resistivity. The resistivity of copper is in ohm meters. That's because the resistivity is measured in, resistance is measured in ohms. If I solve for resistivity, it's resistance times A divided by L. So it's ohms times meters squared divided by M. That's how you get ohm meters for resistivity, because it's the resistance times the area divided by the length. That gives you ohm meters. Area is pi r squared. That's what that is. The length is 0.02. You just calculate the resistance, and what I'm getting is about 0.1 ohms for that little bit of carbon. Carbon is not such a great conductor. It's got one of the higher resistivities of metals. The resistivity, that is a property of the material, where resistance, that depends on the specific shape and size of the sample. Depends on the length and the cross-sectional area.